All right, welcome back, everyone, to this year's hottest event for junior researchers. So we have two talks today. First up, we have Axel Ljungström, who will tell us about calculating a Brunerie number. So take it away.
Oh, thank you. All right. Whoops, can I? Right, so this is a continuation of, I guess, Brunerie's PhD thesis. So he, as you probably all know, Guillaume Brunerie constructed a number n such that pi4 of S3 is equivalent to Z mod n, right? And then what he did later was, in his second half of his thesis, was that he proved that this n is equal to plus or minus 2, and thereby also showing, of course, that pi4 S3 is isomorphic to Z mod 2. So proving that n is equal to plus or minus 2 shouldn't be necessary. So, you know, we're constructivists, we're good constructivists. We have a constructive proof, a constructive definition. So we should be able to just put this n into our proof assistant and just hit enter and see what it spits out. And this is, of course, the famous or infamous problem of computing the Brunerie number. But this is not that easy. So what we had to do instead was, so Anders and I we have formalized this theorem. But then I was a bit annoyed because I still felt like we should be able to at least sort of see y is equal to plus or minus 2 sort of directly. Because, I mean, this number n is constructively defined. In hot, we can really like expand terms and look at what they look like, you know. We can really get sort of first-class access to our objects that we define. So sort of, I wanted to construct a proof by staring, essentially, right? And so today I'm going to present such a proof. So a very direct proof of why n is equal to plus or minus 2. So I'm going to need some basic stuff. So yeah, just to recap, I'm sure most of you have seen these things a billion times before, but I need suspensions. So if you have a type A, you can define a suspension consisting of, it consists of, can you see my mouse, by the way? Yes, okay. 2 points, north and south, and a family of paths married, constructing for each point in A path from north to south. If you'd like push-out diagrams, here's the push-out diagram. It's a homotopy push-out of this diagram. If you're more comfortable with that. So that's suspensions. I'm going to need the circle. So the circle I like to define with a base loop construction. So a base point and a loop from base to itself. Some people prefer susp of bool. I'm not going to get into that debate now. I like this one. It's easier to work with. We can also then define higher spheres by just taking, so the n sphere by taking the n-1 fold suspension of S1. Right. So an important thing here about suspensions is that when you have a canonical map sigma from A into the loop space of the suspension of type A, given that your type is pointed. And so here the loop space of the suspension of A is just paths from north to north. And this is given by mapping A into merit of A. That gives you a path from north to south. And then you want to get back to north. So you compose with merit of the base point of A inverse. So in particular, since we define spheres by suspension, this gives us a map from Sn into omega Sn plus 1. So this version of sigma is very important here. It's very useful. What else? Oh, yes, we need joins. So the join of two types A and B is like a fancy coproduct. So you have a left inclusion from A into the join, and you have a right inclusion from B into the join. But then you have this push constructor saying that for any 2 points in left of A and in right of B are equal up to a path. So you introduce a lot of paths here. So yeah, it's just the push out, the homotopy push out of the projection maps from A cross B. Right. So joints are very central here for what I'm going to do. So I should have introduced this step by step. Sorry about that. But there's a very useful way of constructing maps out of joins. So if you want to construct a map out of A join B into some type C, you can do this by first defining a map A cross B into omega C, and then you can kind of lift it to a map out of the join. So given a function f from A cross B into omega C, we define iota of f. So iota sounds like join, which is of course the way that a Swede would pronounce join. This is, I couldn't come up with a better name for it. Thank you. So what it does, it takes in left of A and in right of B, both to the base point, so it's constant on the inclusions. And then for any, when we apply iota of f to push AB, we have to provide a loop in C, and we just apply f, right? So this is a very sort of nice way of constructing maps out of joins. So let's now note that if we have two functions, f and g from a cross b into omega c, we can compose them by just applying path composition pointwise. So f composed with g at ab would just be fab composed with path composed with gab. So now there's sort of a natural, half natural question. Is this iota a good construction? So is there some way of saying that iota f composed with g is the same as iota f plus iota g, whatever plus means here? And the answer is yes, if a and b are reasonable. So in particular, when a and b are spheres. So just first recall that the nth homotopy group of a type A is the set of pointed maps from the n sphere into A. Now we're going to create this super ad hoc version of homotopy groups. So for n and m, I'm going to define the n plus m plus 1 homotopy group of A with a little, there's a little star here, so it's from the join. So instead of doing it from Sn into A, I'm going to do it from Sn join Sn into A. There's a reason for this, I promise. So what we can show is that there's a group structure on this guy, and this is quite natural because this is actually equivalent to a sphere. But it's also a very nice group structure in the sense that if you have two functions f and g from Sn cross Sn into omega A, you have that this iota construction of f composed with g is actually iota f plus iota g in this group. So we've sort of given some form of meaning to this statement. And this will be used quite heavily in the proof, but implicitly, because I don't have time to go into details, of course. So disclaimer, I've only sort of formalized this for n and m equals 1, but that's actually the only case we need. I also assume that A was 1 connected, I think, because I was being very lazy, but you shouldn't have to do that. Right. Okay, but so let's talk a bit more about this iota construction. So it's so let's, for example, look at the canonical map cup from S1 cross S1 into S2. So there's a very natural map here. I'm calling it the cup product because it kind of looks like a cup product. The idea is that you take the one cell and the one cell in S1, and then you map it to the 2 cell. And if you compose this with sigma, you get a map from S1 cross S1 into omega S3. Now, this is precisely the type of map that we can lift to a map out of a join. So if we apply iota to this composition, we get a map from S1, join S1 into S3. I'm going to call it F because it's so important. It gets capital F. So proposition is that F is an equivalence, and composition by F inverse is what gives you the isomorphism between the strange homotopy groups that I just defined and the original homotopy groups I just defined. Well, for 3, but. And what else did I want to say about this? Yeah, so I mean, it's well known that these two, okay, the title of the slide, it's well known that this equivalence holds, but it's very nice describing this equivalence in this way because it really sort of builds it up from very simple functions. It makes it much more manageable, which we will see later. Okay, okay, good. Now we can get into sort of the good stuff. So here's another, well, here are 2 more iota constructions. So we can define 2 maps H and beta. So H is for Hopf and beta is for Brunerie. I don't know why I didn't call it B. Beta looked nicer, I guess. It goes from, they both go from S1 cross S1 into omega S2. So H, the Hopf guy, will send X and Y to sigma applied to Y minus X. And this is, the minus here comes from the fact that S1 is a topological group, right? And beta will look very similar, but instead we will kind of apply sigma to both arguments and flip them around. So we map X and Y to sigma Y, composed with sigma X. So we have these two maps, and when we apply the iota construction to these guys, we get maps from S1 cross S1, join S1 into S2. So the first guy here, I'm going to call the Hopf map, and the second map here, I'm going to call the Brunerie map. And so here's another thing you can do with these. So if you pre-compose with F inverse, this gives you maps from S3 into S2. And hence we get two corresponding elements. So just with a hat on top, iota H and iota beta in pi 3 of S2. So this is sort of the way you construct elements in this guy. And so fact pi 3 S2 is isomorphic to the integers, and it's generated by the Hopf map. So lifted here by this F inverse, but we don't really care about the F inverse. It's just annoying, and we're going to get it out of the way later anyways. So the Hopf map generates this guy, and what Brunerie showed was that pi 4 of S3, so a different homotopy group, is isomorphic to Z mod n, where n is the integer such that n times the Hopf map is equal to the Brunerie map. And this is what we're trying to show now. We're going to show that this is equal to -2, actually. So I claim that -2, setting n equals -2 solves this equation with the way that I constructed the Hopf map and the Brunerie map. So the proof is a bit silly. So here are some equations. Right, so this is the statement that we want to show. I've just moved the minus sign over to the other side. We want to show that the Hopf map plus the Hopf map is equal to minus Brunerie map. So spelling out what this means, it's the original Hopf map that came from join S1 into S2, composed with this annoying F guy plus itself equals minus the Brunerie map composed with this annoying F guy. So we really want to get rid of this F inverse. So F has a super nice description in terms of this cup product. F inverse is a mess and it's completely unworkable. So we would like to get rid of it. And that's kind of my whole reason for introducing this these weird homotopy groups. Because now when there's meaning to this plus here, we can actually add stuff in the weird homotopy groups. We see that this guy is actually, this is a homomorphism, so we can actually just pull this out on both sides. So this equation here, this mess, becomes this much nicer equation here instead. So what we're going to do now is we're going to look at this equation, and we're going to start passing it through a bunch of isomorphisms until we get something nice. So we're going to start in pi 3 of S2. We're going to move over to pi 3 star of S2, the weird homotopy group of S2. We're going to move over to the weird homotopy group of S1 join S1 and over to the weird homotopy group of S3 along a bunch of isomorphisms. And we'll see that in the end, we will have something that's very solvable, that's very cute and nice to look at, unlike what we have right now. Okay. So I'm just going to sketch how to do this. I don't have any details. I can't go into detail, of course. But yeah, okay. So there's a little roadmap here. So we're starting in here. Our equation looks like this. And now we want to see what happens if we compose with F, the isomorphism between S1 join S1 into an S3. So we want to just take this element and compose it with F, and take this element and compose it with F. And that gives us a corresponding equation, but over here instead. But if you compose these guys with F, well, then you just cancel out F inverse, right? So we end up now, if we move over from here into here, we end up with a new equation that looks like this. So we've completely got rid of this ugly F inverse everywhere. It's very nice because it's, as I said before, completely unworkable. So now we have a much nicer equation lying in here. And we would now like to apply this map to both sides of the equation and see what we get. So this map, so it turns out that if you start in here and you apply you compose with the Hopf map that lands you in here, that's an isomorphism. Now, unfortunately, this is the inverse of this isomorphism, which is also a mess and cannot be understood. I think this guy is actually the reason why the Brunerie number is so hard to compute. However, the map from here into here is very nice. It's just composition with the Hopf map. So what we're going to do is we're going to try to construct two candidates over here and show that if you compose them with the Hopf map, you get the left-hand side and the right-hand side of our original equation. So what I'm saying explicitly is we want to construct two maps F and G from S1 join S1 into itself, such that if you compose F with the Hopf map, you get the Hopf map plus the Hopf map. And if you compose G with the Hopf map, you get the Brunerie map. So F is kind of obvious when you look at it. It's just the identity plus the identity. That solves this kind of trivially. For G, we need something a bit more complicated. Now, you've probably already forgotten how you construct the Hopf map and the Brunerie map. I realize this, but let me just give you the definition of G. So you really don't have to stare at this too much. It's just it's a non-trivial thing to define. It's very surprising that it looks like this, but actually, when you set it up this way and you try to verify that Hopf map composed with G equals the Brunerie map, you see that it kind of just magically works out. So it's sort of a well-chosen thing. It kind of uses the flexibility of the join that you can put things in here. I think I could have phrased this in a better way, but yeah, okay. It kind of just magically works out when you set it up this way. And actually verifying that the G composed with the Hopf map gives you the Brunerie map is almost trivial. You just get the things here cancel out in the right way, and it just becomes the Brunerie map. So that's nice, because now we have reduced our equation to an equation in here. So now we want to show, we're working in here, and we want to show that the identity plus the identity is equal to minus this G guy that I just gave. And let's apply. So this looks like it should be easy, maybe, but G is it's still a mess. So we need to pass it one more time. So this time we're going to just compose with F, the equivalence between S1 join S1 and S3. We're going to pass it along with by composing with F, and we're going to look at what happens. So let's first look what happens when we compose the left-hand side with F. So this thing, well, of course, that just gives you F plus F, right? There's not much happening with the identity function. For the right-hand side, now we want to look at what happens when we compose G with F. My claim is that composing G with F gives you minus F plus minus F. And this might look surprising because F was this nice guy induced by the cup product, and G was this horrible mess. But using the fact that F is defined in terms of the cup product, actually, this whole statement can be reduced to some very basic, and also using, the homomorphism property that I talked about with this Iota guy. The proof just boils down to proving a very basic identity involving this cup product. So, or these two identities. And these follow from some form of graded commutativity and some form of distributivity. So this cup product kind of satisfies all the properties you would expect from a cup product. So these things are actually quite easy to prove, and there you have the proposition. And now we're kind of done, because now we are reduced to verifying. So we show that the left-hand side mapped to F plus F, and that the right-hand side, G, mapped to this guy, now with a minus sign in front. Obviously, the minuses cancel out, and we're done. So if we combine all the things we've done here, we've shown now that that n equals -2 did solve the problem. So the Brunerie number with our definition of it is equal to -2. And so if you pair this together with chapters 1 through 3 in Brunerie's thesis, the theorem we have just shown allows us to conclude that pi for S3 is equal to Z mod 2. So the nice thing about this is, of course, that we're skipping a lot of Brunerie's original proof. So we're skipping all of chapters 4 through 6. And also we're not using any cohomology or homology, which is also nice. So I've been trying to dig up sort of some old literature here. So there are, I guess, two classes of proofs of this statement. They either use cohomology or homology in some way, or they use some properties of manifolds, which we don't have access to now. So maybe this gives you sort of a new proof of this theorem. I've asked people, but nobody can tell me for sure. So I'll be very interested in knowing if anyone knows the full story here. But of course, we still need chapters 1 to 3 in Brunerie's thesis. That's an important thing here. But if we ignore chapters 1 to 3, if we just pretend we didn't know what was going on there, this actually gives you a standalone proof of the fact that if pi for S3 is non-trivial, then pi for S3 is isomorphic to Z mod 2. And the proof of this only uses the fact that the Brunerie number is 2. It uses the Ferdinand suspension theorem to give you a surjection from pi 3s2 onto pi 4s3. And it uses the Ekman-Hilton argument to kind of throw things around a little bit and make things cancel out in a nice way. I'm not going to do it here, but it works out. Now, another version of this guy is that if the suspension of the complex projective plane is not equivalent to S3 wedge S5, then pi 4s3 is equivalent to Z mod 2. And this has to do with the fact that we define CP2 as the suspension of the Hopf map. So there's a link here that I'm kind of just hiding. So this is something that I would be very interested in showing too, because this would give us a completely new proof of it. At least a completely new proof with respect to what's been done in Hopf before. So you can do this easily if you have Steenrod squares, which is a cohomology operation. So this is working process together with David Van, a guy from Gothenburg, from Chalmers. But of course, I would really like to see a direct proof of this too that doesn't use Steenrod squares, because then you would get a proof completely of pi for S3 equals to Z mod 2 completely without cohomology, which would be super cool. So if anyone knows how to prove this, has a very good idea for how to prove this directly, then I would be very interested. Right. So future work, show this in a nice way. So I would actually say that we have already the tools we need to prove this using Steenrod squares, but I would like to do without two. That would be much cooler. And so I should also mention that the Brunerie map is just one example of something called a Whitehead product. So this is a map that goes from pi n of x to pi and pi m of x into pi n plus m minus 1 of x. So these play an important role in homotopy theory and in the computation of homotopy groups of spheres. So it would be interesting to see, I mean, since we've sort of computed one Whitehead product now by looking at this Brunerie map. So it would be interesting to see how this extends to well, a more general setting. If we can get other Whitehead products too in the same sort of primitive fashion that we've done here. Now I forgot to put a last slide that says thank you for listening or something, but that's what's supposed to be there. So, thank you.
Okay. Thank you, Axel. Let's all visually applaud for the speaker. And does anyone have questions or suggestions? I guess I'll start. So if you go back one slide.
This slide?
Yeah. So the if pi4 of S3 is non-trivial, that's a sort of thing I could imagine that there's some like really smart way to prove that directly using univalence, right? Like
Yeah.
you could kind of say, well, if it was trivial, then true would equals false by some very bizarre transport that you would just cook up or something, right?
Yes.
I have no idea what that would be. Just I could imagine there being some like direct proof of that. Yeah.
Yes, I have tried hard.
Sure.
So what you need is some form of map from this guy into Boole. It's just so incredibly unclear what this map would look like.
Right.
Definitely univalence will pop up a lot, but so for me the easier statement was this statement, which might actually be harder, probably, unfortunately. So yeah, but no, I've tried it and failed many times.
Yeah, fair enough. So there's a question in the chat saying plus was just addition, right? Like addition of natural numbers, right? I'm not sure which.
This plus here.
I'm not sure.
So it might be, I use plus a lot, so maybe that was
right.
it. Yeah, so I'm sorry about this. Yeah, so here the minus, for example, is actually in S1, and these pluses here are the pluses in the homotopy groups, which are numbers, because all the homotopy groups here are isomorphic to the integers. So you can think of it that way, but I think it's the plus in the homotopy group. So sorry, I should maybe have made that clearer.
Okay, yeah. The question asker, Ian, says thanks.
Okay.
Any last question? Okay, well, let's thank Axel again, and we'll see you again in half an hour.
Mm-hmm.